Welcome to this lecture on moisture balance analysis in building physics. In this video, we will work through a complete four-step calculation to determine the steady-state indoor relative humidity of a newly constructed apartment and assess whether condensation risk is present. We begin by identifying the boundary conditions and all moisture sources acting on the space. The studio apartment has a volume of 75 cubic meters and is heated to an indoor set point of 21 degrees Celsius. The construction comprises cast in situ concrete walls and a large single-glazed window. The external boundary condition is outdoor air at -2 degrees Celsius and 90% relative humidity. This cold, damp air enters the space through the ventilation system. The first internal moisture source is built-in moisture. The freshly cast concrete walls are still curing and release moisture at a rate of 20 grams per hour until they reach hygroscopic equilibrium with the indoor air. The second source is the occupant load. Residential activities, cooking, breathing, and drying laundry indoors, contribute a combined total of 120 grams of moisture per hour. The mechanical exhaust fan operates at 0.5 air changes per hour. For this volume, that corresponds to 37.5 cubic meters per hour, or approximately 45 kilograms of dry air per hour. Ventilation removes moisture-laden indoor air and replaces it with outdoor air, making it the primary moisture removal mechanism. All four moisture inputs are now defined. We proceed to the quantitative analysis. We calculate the external vapor pressure and the total internal moisture generation rate. Step 1. We determine the saturation vapor pressure at the outdoor temperature of -2 degrees Celsius. The empirical formula gives Psat as 288.68, multiplied by the quantity 1.098 plus T divided by 100, raised to the power of 8.02. Substituting T equals -2, Psat evaluates to approximately 517 pascals. The actual outdoor vapor pressure PVE is the product of the relative humidity and the saturation pressure. PVE equals 0.90 multiplied by 517, giving an actual outdoor vapor pressure of 465 pascals. Step 2. Applying the conservation of mass principle, the total moisture generation rate G total equals G built plus G int, the sum of all internal generation sources. Substituting the values, 20 grams per hour plus 120 grams per hour yields a total internal generation rate of 140 grams per hour, which is equivalent to 0.14 kilograms per hour. Both the external vapor pressure and the total moisture generation are now determined. We advance to step 3. We apply the steady-state mass balance equation to determine the indoor specific humidity. The governing equation states that the indoor specific humidity Xi equals the outdoor specific humidity Xe, plus the ratio of total moisture generation G total to the ventilation air mass flow rate Ga. This equation expresses the equilibrium between moisture input, internal generation, and moisture removal by exhaust air. We first calculate the outdoor specific humidity Xe. Using the ideal gas law for water vapor, the outdoor vapor density ρV equals PdE divided by RV times Te. That is 465, divided by 462 times 271.15, which gives approximately 0.0037 kilograms per cubic meter. The outdoor specific humidity Xe is the ratio of vapor density to total air density. Dividing 0.0037 by 1.2 gives Xe equal to 0.0031 kilograms of moisture per kilogram of dry air. Substituting into the mass balance, Xi equals 0.0031 plus 0.14 kilograms per hour divided by 45 kilograms per hour. This evaluates to an indoor specific humidity of 0.0062 kilograms per kilogram. Note that the indoor value is exactly double the outdoor specific humidity. This reflects the significant combined moisture generation relative to the available ventilation capacity. The indoor specific humidity is determined. We now proceed to the final step. We convert the indoor specific humidity into relative humidity through a sequential three-stage process. The conversion proceeds from specific humidity Xi, to vapor density ρVi, then to vapor pressure PVi, and finally to relative humidity Phi. Stage 1. The indoor vapor density ρVi equals Xi multiplied by the density of air ρA. That is 0.0062 times 1.2, giving 0.00744 kilograms per cubic meter. Stage 2. Applying the ideal gas law, the indoor vapor pressure PVi equals ρVi times RV times Ti, substituting 0.00744 times 462 times 294.15, this gives approximately 1011 pascals. Stage 3. Using the same empirical formula, the saturation vapor pressure at 21 degrees Celsius evaluates to approximately 2487 pascals. The indoor relative humidity Phi is defined as the ratio of actual vapor pressure to saturation vapor pressure at the same temperature. Phi equals 1011 divided by 2487. This yields a steady-state indoor relative humidity of 41%. A value of 41% falls within the recommended indoor comfort range of 40 to 60% relative humidity. No bulk condensation risk exists at the indoor air temperature. However, localized condensation may still occur on cold surfaces such as the glass window, where surface temperatures may fall below the dew point temperature. We now present the complete summary of all results. This table presents all intermediate and final values from the 4-step analysis. The outdoor vapor pressure is 465 pascals. Total moisture generation is 0.14 kilograms per hour. The outdoor and indoor specific humidities are 0.0031 and 0.0062 kilograms per kilogram, respectively. The indoor vapor pressure is 1011 pascals, against a saturation pressure of 2487 pascals. The resulting steady-state indoor relative humidity is 41%. This concludes the moisture balance analysis. In the next lecture, we will extend this framework to assess condensation risk on the building envelope using the dew point criterion. Thank you for watching.